This is Physics 102B at Porterville College, Chapter 21 Homework Solutions, starting with number 49. The question asks, for which material in the table given in the textbook does light travel more slowly? What is that speed? The index of refraction is a measure of how much light gets slowed down through that medium. So the one with the highest index of refraction is diamond with 2.42. So here's the formula right here. The velocity is going to be the speed of light divided by n. So 3 times 10 to the 8th meters per second divided by 2.42, and we get 1.24 times 10 to the 8th meters per second. And the answer in the back of the book is incorrect. Number 50 gives the speed through a certain medium, and we're to find the index of refraction. So index of refraction is c divided by v. 3 times 10 to the 8th meters per second divided by 2.11 times 10 to the 8th meters per second, and we get an index of refraction of 1.42. Number 51 has for 4 different materials: ice, quartz, ethanol, and diamond. What is the speed that light travels through those 4 media? And you use the equation v equals c over n. Plug in the n, the index of refraction that's given in the table in the book, and that's listed there on the screen. And you get those answers. Part C in the back of the book is incorrect. The answer for part C, ethanol, is 2.21 times 10 to the 8th meters per second. My guess is that whoever wrote the book, wrote the answer key, accidentally made the index of refraction 2.36 instead of 1.36. Number 52 involves a flashlight shining down into the water. It makes an angle of 55 degrees as it's hitting the water through the air. And the question is asking, what is the angle from the normal as it goes through the water? So I advise you to set this up the way I've shown you in class. You draw the picture, identify on this side that the one medium is air and the other is water, and I like to write the index of refraction next to it, and I specifically write n1 and n2. That way, as I'm in the midst of plugging the values into my formulas, I don't lose track of what n1 and n2 and all the different variables are. So once I've drawn the picture, I apply Snell's law. We're solving for theta 2, so this is really just a matter of algebra, a little trigonometry with algebra. I solve for sine theta 2. Once I get that as 0.6159, then I take the arc sine of that, and I get 38 degrees. It's also helpful, when we're setting up the picture, to have a sense of what we expect is going to happen. Remember what I taught you in class, that light will bend closer to the normal in a medium where it's slowed down. So I've tried to draw approximately a 55-degree angle for theta 1. And for theta 2, I don't know what it should be before I solve analytically, but I know that it should be closer to the normal, so I draw it like that. And so when I get an answer to this problem of 38 degrees, I'm confirmed in my picture that I was expecting an angle less than 55 degrees. Number 53 is a case in which there are 2 places where the light goes from one medium to the next. So in this more complex picture, I've drawn it. I've drawn my air, water, and glass. And this time for air, I'm making that n1, water is n2, and glass is n3. As I've drawn the angles, I expect that going from air to water, theta 2 is going to be smaller than theta 1. Looking at the indices of refraction between water and glass, N2 and N3, since N3 is greater, that tells me light is going to be even slower through the glass. And so I've drawn my angle even smaller for theta 3. So I'm expecting theta 3 to be pretty narrow. Well, the question is asking, first, what is theta 2, and then what is theta 3? So I solve for theta 2 the same way I did in the previous problem, using Snell's law, and I get 14.9 degrees. Then, as the light goes from the water to the glass, from region 2 to region 3, I set up Snell's law, and now I can just forget about region 1. Snell's law now becomes N2 sine theta 2 equals N3 sine theta 3. So I solve for sine theta 3 the same way I solve for sine theta 2. And what I get is 12.9 degrees. And by the way, as an added bonus to this question, what you may want to do is prove to yourself that it's as if the water weren't even there. If the light just went from air straight into the glass without any water being there, it would still go through at 12.9 degrees. Now, you can prove that to yourself, one, by plugging in the actual numbers, or two, and just take the case of light going straight from air to glass. Or another way you could do that is do this same problem, but without plugging in the numbers. Meaning, right here, sine theta 3 is N2 over N3 times sine theta 2. Well, how do we know what sine theta 2 is? Back up here, it's N1 over N2 times sine theta 1. And when you do that without even plugging in numbers, you'll see that the N1 should cancel out. So that's just a good extra bonus you can do. Let's go to number 57 now. This is the problem regarding looking at a fish underwater. There's some geometry to this beyond just the solving of Snell's law. So what we have is same as the previous two problems, where we're just simply looking at what is the angle theta 2 as it goes through the water. And so right here, I've solved for it. I've abbreviated it because the solution is pretty much the same one we followed in the last two problems. But you should get that theta 2 is 32.12 degrees. The problem is asking how far horizontally is the observer away from the fish. And you can see I've set up my picture a little differently. I've added some lines because in the end we want to know what is the length of this leg of the triangle, the horizontal leg, plus the length of this horizontal leg. So this is just a little bit of geometry and trigonometry. Now that we know theta 2 is 32.12 degrees, let's take a look at this. The first triangle, if it's a 45-45-90 triangle, if this leg is the vertical leg is 0.52 meters, the horizontal leg is also 0.52 meters. It's an equilateral right triangle. For this triangle, if that's a 32.12 degree angle, we know that the vertical leg is 0.65 meters. We want to know the horizontal leg. We'll call it x. Well, in that lower right triangle, let's set up this trigonometric ratio. The tangent of the 32.12 degree angle is equal to opposite over adjacent, x over 0.65. So we solve for x, and we get that it's 0.408 meters. So the distance from the observer to the fish is 0.52 meters plus 0.408 meters, and that gives us, we'll round it with significant figures, 0.93 meters. Problem 63 is the beginning of the lens problems. I show in problem 63, even though it only says the instructions are just to do some ray tracing, I solved this analytically as well, just so you can see that usually in these problems you only need to do one or the other, but they complement each other. And it's a good idea to do them both and see that the geometric picture that you draw and the analysis from the equations, that they confirm each other. So number 63 says focal length of 50 centimeters. Draw a ray diagram to show, first of all, an object at 150 centimeters. The thing I like about the graph paper and using a ruler is we can do a scale drawing. So I've drawn, I think every one of these little squares is 20 centimeters. So here's one focal length at 50, at 100, and then my object is at 150. And here are these focal points again at 50, or 50 is the focal point, but then I just tack out the focal lengths to give me a scale to draw by. So here's my object, and I draw two rays. The first light ray goes parallel to the principal axis. When it hits the lens, it converges straight through the focal point. The second ray that I draw goes from the top of the object straight through to the middle of the lens. Any light ray that goes through the middle of the lens will not bend. It'll just keep going straight. And where those light rays converge, that's going to be where the image is. It's a real image. It's inverted, and it's reduced in size. And that will always be the case when your object is beyond two focal lengths. So there's where I've drawn it. Now, just for fun, I've also done the math, the thin lens equation. We're given the focal length and the object distance. You can do some algebra there, solve for image distance. It gets 75 centimeters, and that's approximately where this is. That's going to be 20, 40, 60, 70, and a little bit more. So it's about 75 centimeters. My picture confirms that. The magnification, negative of distance image over distance of the object, negative 75 centimeters over 150 centimeters, shows the magnification is negative 0.5. Negative means it's upside down. That's what my picture shows. 0.5 means it's half the size of my object. And that's pretty good. My object, I drew it as 2 squares, and my image is 1 square. So you can see how the math confirms the picture that I've drawn. Let's go to part B. Part B says that the object needs to be 80 centimeters away, and this is a case where it's between 1 and 2 focal lengths. There I've drawn the picture, same as before. One light ray goes parallel to the principal axis, converges through the focal point. The other light ray goes straight through the middle. Where those light rays meet is going to be the top of our object. And so what I see there is an inverted image that is enlarged. The math behind it that I've done, you can do the math on your own. I don't show the solution to it, but just here's the answer, the final answer. The image distance should be 133.3 centimeters. Magnification I can get from negative image distance over object distance, and I get negative 1.67. Part C is a case where the object is very close up. This would be like in the case of a magnifying glass. This is going to be a virtual image. As we do the lens tracing, or the ray tracing rather, the first ray goes parallel to the principal axis through the focal point. The second ray goes straight through the middle. They actually diverge on that side, but you trace them back, the imaginary lines from those rays, and they will converge on each other right here, and that's the top of the image. So what we get is an enlarged image that is virtual. Okay, the next problem is number 66. 66 says a convex lens forms an image of a 12 centimeter tall soda can. Okay, so that's the height of my object, 12 centimeters. The image is 2 centimeters tall and appears 8.2 centimeters from the lens. Okay, those actually just give absolute values. We need to think about whether those are negative or positive. Height of the image and distance image, without putting a little thought into it, I don't yet know whether either of those are positive or negative. But so I need to think about the three cases of where the object is in relation to the focal point. And if you look in your book, there's a page where it shows one page is devoted to this, the different cases. But the case where the object distance is greater than twice the focal length, that's the case where it's going to be an inverted real image. So the fact that it's 2 centimeters tall, that the image is 2 centimeters tall, the only case where that happens, where you get a reduced image, is in this case, if you look at that chart in the book. So I know that it's going to be inverted and real. That's why I can say that the height of the image is -2 centimeters. Again, for a convex lens, if it's reduced, it's going to be an inverted real image. And since it's real, this is the case where the image distance is positive. The question is asking, what is the object distance and the focal length? Well, you can solve for magnification and get that by the ratio of the height of the image over the height of the object. You get -1/6. From there, you can use that magnification of -1/6 or -1/6 is equal to the negative of distance of the image over distance of the object. So we get object distance of 49 centimeters. Then you can use the thin lens equation, and we plug in the numbers to find the focal length. 1/f is 1 over object distance, 49 centimeters, plus 1 over the image distance, which is 8.2 centimeters, and you solve for the focal length of 7.02 centimeters. By the way, I've drawn down below a scale drawing of the ray diagram, and this is what it should look like. Number 67. Using a 20 centimeter focal length convex lens to image a small light bulb, where should you place the bulb to get a half-size real image? And where is that image? Okay? Half-size real image. Magnification is 0.5. Now a real image is always inverted, so it's going to be -0.5 magnification. Let's now come over to the right-hand side. Magnification is -di over do. So do is -di over m. Remember, m is -0.5. So do is going to be, if we're dividing by -1/2, do becomes 2 times the image distance, which means that the image distance is 1/2 the object distance. Now let's apply that expression to the thin lens equation. Right here I've just plugged in directly 1 over f, 1 over 20 equals 1 over do, 1 over do plus 1 over di, and I've done this replacement that we had up here. If di is 1/2 of do, 1 over di is 2 over do. So we have 1 over 20 is 1 over do plus 2 over do, which is 3 over do. If 1 over 20 is 3 over DO, then DO becomes 60 centimeters. And DI is half of that, so it's 30 centimeters. Since it's positive, that means it's on the other side of the lens. Number 67, part B on 67 says, where should you place the bulb to get a double size real image? Instead of a half size, now we have double size. It's the same procedure mathematically. Magnification is now negative 2.0. So we can say magnification is negative di over do, so do is negative di over m, which means it's di over 2. I want to solve for di, so di is twice do. Plugging into the thin lens equation, 1 over f is 1 over do plus 1 over di, but let's make di 2 do. So 1 over f is 1 over do plus 2 do. Let me start that again. 1 over f equals 1 over do plus 1 over 2 do. Doing the math, adding those fractions, you get 3 over 2 do. And now we solve for do. do is 3 halves f, which makes it 3 halves of 20 centimeters is 30 centimeters. di is twice that, so the image is 60 centimeters on the other side of the lens. Number 73. You're using a convex lens with 11 centimeter focal length to study an insect. How far from the insect should you hold the lens? So it's asking, what is the object distance? To get an upright image magnified by a factor of 1.8. An upright virtual image. Look back on the chart in the book of the different cases, and it's the case where the object distance is closer than the focal point. di in that case is going to be negative. Our numbers we can start with are f equals 11 centimeters and m equals positive 1.8, positive because it's upright. So to solve for do, we have this equation right here that di over do is the negative of magnification. So let's solve for di. It's negative mdo. And plug that into the thin lens equation. So di is replaced with, hold on, just zoom in a bit here. di is replaced with mdo. We do some algebra there. I would factor out 1 over do. And that gives 1 over do times 1 minus 1 over m. Solve that algebraically for do, and we get do is f. F times 1 minus 1 over m. Plug in the numbers at this point. So you have 11 centimeters times 1 minus 1 over 1.8, and we get an answer of 4.89 centimeters, which means we need to hold the lens 4.89 centimeters away from the insect. That's the end of the Chapter 21 homework.